Construction and working principle of synchronous motor. What is a synchronous motor? A synchronous motor, short for synchronous electric motor, is an AC motor where the rotation of the rotor or shaft is synchronized with the frequency of the supply current. That is, the rotation period of the rotor is equal to the rotation field of the magnetic machine it is inside of. Let's take a step back for a moment and define what an electric motor is. Electrical motors are an electromechanical device that converts electrical energy to mechanical energy. Based on the types of input, we have classified it into single-phase and three-phase motors. The most common type of three-phase motor is synchronous motor and induction motors. When three-phase electrical conductors are placed in certain geometrical position, that is, in a certain angle from one another, an electric field is generated. The rotating magnetic field rotates at a certain speed known as the synchronous speed. If an electromagnet is present in this rotating magnetic field, the electromagnet is magnetically locked with this rotating magnetic field and rotates at the same speed as the rotating field. This is where the term synchronous motor comes from. As the speed of the rotor of the motor is the same as the rotating magnetic field, it is a fixed speed motor because it has only one speed, which is synchronous speed. This speed is synchronized with the supply frequency. The synchronous speed is given by ns equal to 120 f by p, where n is the synchronous speed in rpm, f is the supply frequency in hertz, p the number of poles. Construction of three-phase synchronous motor. Similar to DC machines where there is no construction difference between a generator and motor, there is no difference between the construction of synchronous motor and the alternator, both being the synchronous machines. The synchronous motor construction is basically similar to rotating field type alternator. It consists of two parts. First one, stator, consisting of a three-phase star or delta connected winding. This is excited by a three-phase AC supply. Second one, rotor. Rotor is a field winding, the construction of which can be saline, projected core or non-saline, cylindrical type. Particularly, most of the synchronous motor use saline, that is, projected pole type construction. The field winding is excited by a separate DC supply through slip grab. Working principle of synchronous motor. Synchronous motor work on the principle of magnetic locking. When two unlike poles are brought near each other, if the magnets are strong, there exists a tremendous force of attraction between those two poles. In such condition, the two magnets are said to be magnetically locked. If now one of the magnets is rotated, the other also rotates in the same direction with the same speed due to the force of attraction, that is, due to magnetic locking condition. The principle is shown schematically in the below figure. So to have the magnetic locking condition, there must exist two unlike poles and magnetic axes of two must be brought very close to each other. Let us see the application of the principle of synchronous motor. Consider a three-phase synchronous motor whose stator is wound for two poles. The two magnetic fields are produced in the synchronous motor by exciting both the winding stator and the rotor with three-phase AC supply and DC supply respectively. When the three-phase winding is excited by a three-phase AC supply, then the flux produced by the three-phase winding is always of rotating type. Such a magnetic flux rotates in space at a speed of called synchronous speed. The magnetic is called a rotating magnetic field. The rotating magnetic field creates an effect similar to the physical rotation of magnets in space with synchronous speed. So stator of the synchronous motor produces one magnet which is as good as rotating in space with the synchronous speed. The synchronous speed of a stator rotating magnetic field depends on the supply frequency and the number of poles for which stator winding is wound. If the frequency of the A supply is f hertz and stator is wound for p number of poles, then the speed of the rotating magnetic field is synchronized given by ns equal to 120 f by p rpm. In this case, as the stator is wound for say 2 poles with 50 Hz supply, the speed of the rotating magnetic field will be 3000 rpm. This effect is similar to the physical rotation of 2 poles with a speed of ns rpm. For simplicity of understanding, let us assume that the stator poles are n1 and s1, which are rotating at a speed of ns. The direction of rotation of the rotating magnetic field says clockwise. When the field winding of the rotor is excited by a DC supply, it also produces two poles. Assuming rotor construction to be two poles, saline type, let these poles be Ns, N2 and S2. Now, one magnet is rotating at Ns, having poles N1 and S1. While at start, rotor is stationary, that is, second magnet is stationary, having poles N2 and S2. If somehow the unlike poles N1 and S2 or S1 and N2 are brought near each other, the magnetic locking may get established between stator and the poles. As stator poles are rotating due to magnetic, rotor will also rotate in the same direction as that of stator poles, that is, in the direction of rotating magnetic field, with the same speed, that is ns. Hence, synchronous motor rotates at one and only one speed, that is synchronous speed. But this also depends on the existence of magnetic locking between stator and rotor poles. Practically, it is not possible for stator poles to pull the rotor poles from their stationary position into magnetic locking condition. Hence, synchronous motors are not self-starting. Why synchronous motor is not self-starting? Consider the rotating magnetic field is equivalent to the physical rotation of two stator poles N1 and S1. Consider an instant when two poles are at such a position where the stator magnetic axis is vertical along AB as shown in the below figure A. At this instant, rotor poles are arbitrarily positioned as shown in the below figure. At this instant, the rotor is stationary and unlike poles will try to attract each other. Due to this, rotor will be subjected to an instantaneous torque in the anti-clockwise direction, as in figure A. Now stator poles are rotating very fast, that is at a speed of ns rpm. Due to inertia, before rotor hardly rotates in the direction of anti-clockwise torque to which it is subjected, the stator poles change their positions. Consider an instant half a period later where stator poles are exactly reversed, but due to inertia, rotor is unable to rotate from its initial position. At this instant, due to the unlike poles trying to attract each other, the rotor will be subjected to torque in the clockwise direction. This will tend to rotate the motor in the direction rotating magnetic field. But before this happens, stator poles again change their positions, reversing the direction of the torque exerted on the rotor. As a result, the average torque exerted on the rotor is zero, and hence the synchronous motor is not self-starting. Methods of starting of synchronous motor. Number 1. Motor starting with an external prime mover. Synchronous motor are mechanically coupled with another motor. It could be either three-phase induction motor or a DC shunt motor. Here, we do not apply DC excitation initially. It rotates at speed very close to its synchronous speed and then we give the DC excitation. After some time, when magnetic locking takes place, supply to the external motor is cut off. Number 2, damper winding. In this case, the synchronous motor is of saline pole type. The additional winding is placed in the rotor pole face. Initially, when the rotor is not rotating, the relative speed between damper winding and rotating air gap flux is large and an EMF is induced in it, which produces the required starting torque. As speed approaches synchronous speed, EMF and torque are reduced, and finally, when magnetic locking takes place, torque also reduced to zero. Hence, in this case, the synchronous motor first runs as three-phase induction motor using additional winding, and finally it is synchronized with the frequency. And now, last but not the least, applications of synchronous motors. The application of synchronous motors include: number 1, a synchronous motor having no load connected to its shaft is used for power factor improvement. Owing to its characteristics to behave at any electrical power factor, it is used in power systems in situations where static capacitors are expensive. Number 2, synchronous motor finds application where operating speed is less, around 500 rpm, and high power is required. For power requirement from 35 kV to 2500 kV, the size, weight, and cost of the corresponding three-phase induction motor are very high. Hence, these motors are preferably used. For example, reciprocating pump, compressor, rolling mills, and etc. Now here we have discussed construction and working principle of synchronous motor. Thank you.